Good afternoon, everyone. I'm very pleased to welcome all of you to our closing keynote for the Welcome Week here in the Department of Electrical and Computer Engineering at the University of Texas at Austin. I'm Diana Marculescu, I'm the chair of the department, and it is my deep pleasure to introduce our keynote speaker. Daniel Cooley is the Chief Technology Officer of Silicon Labs, and he's responsible for the company's overall research and development strategy and execution. Daniel is a respected IoT industry visionary and has been instrumental in building the unmatched breadth and depth of the company's wireless connectivity portfolio. Before joining Silicon Labs, or in this capacity, Daniel served as the Senior VP and Chief Strategy Officer, where he led Silicon Labs' overall strategy, corporate development, M&A, emerging markets, and security. And prior to that, Daniel led Silicon Labs' IoT business as Senior VP and General Manager. Since 2005, he has served in a variety of engineering and business leadership positions at Silicon Labs in the US, Asia, and Europe. We have Daniel here because he's a Texas ECE alumnus. So he holds a master's in electrical engineering from Stanford University and a bachelor's in electrical engineering from UT Austin. He holds 4 patents in radio and low power technology. He currently serves on the board of directors for the Open HW Group, Thinkery, Texas 4000, and the Austin Symphony Orchestra. And he also advises startups in the Austin area. And I know he also plays an instrument, but I'm not gonna say more than that. Without further ado, I'm gonna give the floor to Daniel. Daniel.
Thank you, Diana, and welcome everybody. It's great to be here today to talk with you. I'm looking forward to getting into the presentation right now, but I wanted to mention before then that I'm here for you today, and I do see the questions, the Q&A panel. So if you have questions while I'm presenting, feel free to raise your hand or to go ahead and type that in, and might hit that live. So let me go ahead and get started. Perfect. Okay, so like Diana said, I am the CTO at Silicon Labs, and today I'm going to be talking to you about connecting some dots together. This is going to be multidisciplined around technology, products, as well as your overall career management. Some things to think about, especially as you're in your collegiate part of your careers. I'm the CTO at Silicon Labs. We are a local or Austin-based semiconductor company focusing in on building the solutions for the Internet of Things. So these are chips, embedded software, and tools that make it easy for any company to connect their product to the Internet. We'll talk more about what that means in a second. And you see my email address down there. If you have any follow-up questions you'd like to get into, feel free to send that along. So first, a little bit about myself. Dion did a great job covering it, but I live in Austin with my family, my wife, and I have 3 boys. This picture is about a year old, middle of the pandemic, went right after our baby was born. So we have a busy house, as you can imagine. And I've split my career into 3 going into 4 phases. First, in core chip design, doing mostly analog RF front ends on radio systems. Second, a move into more of the commercial side of our business in product management and ultimately the general manager of our IoT business. I then moved into the chief strategy officer role for the company, leading strategy and M&A, IT and security. And recently, earlier this year, stepped into the chief technology officer role. Over this time period, I've had the opportunity and been very fortunate to live in Asia and Europe, in China, Singapore, and Norway. Those are very formative experiences for me in my career, and still carry a lot of the stuff from those times through to today. I got my bachelor's at UT in 2004 from ECE school, and my master's at Stanford, studying with Tom Lee and Boris Merman in chip design. So we're going to start in the technology portion of this presentation. And it's around an idea that there's something interesting going on in the embedded side of our industry. And when I say our industry, I mean not just semiconductors, but technology in general. Embedded, which I'm calling IoT here, is very different than the other aspects. Sorry, I get my laser pointer. The other part of the technology ecosystem, which is really, I'm just dividing in 4 phases for simplicity here. Big things like data center environment, your desktop PCs, your smartphones that you carry with you, and then everything else, and that's the embedded piece. And you can see some of the factors here: storage, power, battery life, cost, connectivity, and these things are different by orders of magnitude, actually. And the only common thing really about them is that we do interesting work there. We build chips and we build software as an industry across them, but they do very different things in the end. And I liken that to an analogy in transportation around getting things from point A to point B. And if the data center is a fixed high-speed rail network with very tight deadlines and moving big data, big things fast, the PC is the workhorse, the trucks that are driving around the highways. And the smartphones are highly optimized, like performance bikes, like the MotoGP Ducati that you see there. And then embedded is the e-bike, which has its own set of complexities and constraints. So we have to do in IoT, in the embedded side, many of the different kinds of functionality you see elsewhere, but with much less memory, much less power, much longer lifetime, much lower costs, and frankly, with a lot less ability to actually get to those devices on connectivity. The idea of updating an app on an embedded device like you do on your mobile phone on a daily basis doesn't exist. So we have to engineer differently down there. So it's massively constrained. And by the way, last year, Mark Papermaster gave a great talk at this exact forum, focusing more on the data center PC side. He's the CTO at AMD. It was a great talk. You can find it on YouTube. I encourage you to go listen to it and actually compare and maybe contrast some of the things that I'm saying here. So if we turn our attention back to the embedded side, this Internet of Things, there are 4 major initiatives that are underway in the world that are enabling it. And we're starting to get to the dots. We're starting to connect some things here. I know they're boxes, not dots, but you'll see more dots later. The 4 are that we already have ubiquitous embedded computing everywhere. So we have embedded computers that are more powerful than the PCs in the 90s, sitting inside of things like thermostats and light bulbs and door and window sensors and electric meters. These things are already everywhere. We'll talk about why that is in a second. Device makers want to connect those devices, going to the left, to the right here. They want to connect those devices to the internet. And you may say, why the heck would you want to do that? We'll walk through that. Moving down, we also have a very mature infrastructure at this point to get the data off those devices and up to the cloud or wherever they need to live. So without mobile cloud infrastructure and the internet itself, that wouldn't be possible. And finally, the barriers to actually connecting these products to the cloud are in free fall. It's much easier to do today than it was even 5 years ago. So we're going to line these up and we're going to show what will happen in the market. But it starts with data. So first things first, are these computers everywhere? And when I mean embedded computing, I mean a microcontroller. So a microcontroller with memory, with CPU, with I/O peripherals, a computer on a chip is essentially what it is. And this is a 30-year view of the MCU shipments, the actual MCU shipments. And you can see that it starts off in about 2 billion unit range back in 1991 and has ramped pretty consistently over the years to approaching and actually now more than 15 billion units a year. So you have 15 billion computers shipping a year. And you know, if you add up all the other computers, the PCs, the handsets, the data center, the server blades, all that, it is still smaller than these computers going everywhere. And as an example, someone recently took an IKEA light bulb and put Doom on it. I mean, there's a common thing in the world to see what you can put Doom on, and they put the video game Doom and ran it on one of these light bulb computers, which is kind of give you an idea of what you can do with them. So, it wasn't always up and to the right. You see some things happen. The dot-com bust, which if you're old enough to remember, was a very big deal. That's when I was in college. I was living through that. We have the global financial crisis here, very big discontinuity. And then very recently, we had really what amounted to a cycle pop around geopolitics with China and US and trade war in 2019. And the pandemic isn't even on this. But we won't go into that during this talk. But yeah, at this point, it's fairly safe to say these computers are everywhere. And we'll talk about why they want to get connected. So when we got into this business about 10 years ago at Silicon Labs, I was part of that, and the use cases were fairly narrow, but we could see them getting really, really big over time, almost to the point where every embedded computer, every MCU on the Earth was a candidate to connect to the internet. And over the years, I've collected a few reasons why. Why is that? Why would someone want to take something as simple as a light bulb and connect it? And these are just 10 of the reasons here. Everything, I'm not going to read through every single one of them, but it's touching almost every part of our economy and the fundamental drivers for it. I mean, first and foremost, people want it. You want your TV now connected to the internet. And that just wasn't the case 10 years ago. An internet connected TV was a very rare thing. But now you wouldn't buy it unless you could get your YouTube or your YouTube or your Netflix or whatever directly on it. There are new use cases coming out all of the time with an internet connected device, such as the voice assistants. I remember getting my Alexa for the first time, and it was kind of like magic, something that I grew up, watching Star Trek, wanting to talk to a computer, and here I was finally able to do it. We take it for granted now, but it was a very big deal. So these are very consumer driven, over here, but there's so many more reasons for the IoT to emerge, from total cost of ownership and lifetime, government compliance, shelf labels. You may say, how the heck is a shelf label allowing you to do government compliance? But a simple example, a few years ago, I'll pick on Whole Foods because they're an Austin company here, and Whole Foods got sued by Massachusetts state government because there was a big price discrepancy between the shelf and the register, and obviously in the wrong direction. So someone would see a product on the shelf, maybe $1, and go to the register, and maybe it was $2. And so they rolled out electronic shelf labels to drive very tight alignment between the pricing in their systems and the pricing on the shelf. So that's just an example. Beyond that, things like efficiency. We see a lot of agricultural pickup, plants, but also livestock. I mean, cows are very expensive animals. They are very valuable to the farmers, and people want to sense, what's the cow doing? Where is the cow? Is the cow sick? Are they eating? Are they eating the right things and stuff like that? So we're seeing a lot there. Safety, reliability, new business models. Every company on the planet making things now is thinking hard about what an internet connected device allows them to do. And that just wasn't the case in the past. Convenience, simple example, your AirTag. I don't know if you have these. I don't know where mine is right now, but finding your stuff. Where is my stuff is one of the biggest questions. I have 3 kids in my house, and where's my stuff? It comes up almost every day. Where are my keys? Where is the remote? Where's the dog? Other industries here, like insurance, can lower their costs, lower their premiums if they can detect things sooner. Water leaks is a very big example. Lastly, revenue. You can actually drive revenue through an IoT device. This is actually a shelf label, believe it or not, but you can market it. You can show sales. You can do a lot. So there's a lot more than this in the world for IoT devices, but I haven't come across one industry that can't benefit. So we're seeing big pull from our customers for sure. It's not enough to want to connect your device. You have to actually get the data out and into the cloud and manage it. So you need a lot of infrastructure to do that. And that infrastructure now is here. And the way I went out and tried to find my data was I was like, how many people are using the internet overall? How many smartphones are there? Because that's the primary interface to the IoT. And then where is the data going? When is cloud going to get bigger than on-prem data center? So what we can see now is that about 2/3 of the people on the planet are using the internet. 2/3, 2 out of every 3 people on the planet. And this includes children, by the way. If you just think about the adults, it probably is bigger percent. So if you're not using the internet, you probably know someone who is. And so you can use that as a good gauge of the maturity there. On the smartphone side, we're starting to see about half, 1 out of every 2 people on the planet is using a smartphone. And that just wasn't the case even 10 years ago. Most people on the planet maybe had a phone, but it was a feature phone, or it was a simple device to make phone calls, not send data around. These things we have now are primarily pocket computers more so than phone. So yeah, about 3.5 billion people on the planet now using a phone. So you either using a phone, or on average, if you're not, the person next to you is. And lastly, and this is probably the single biggest lever that is happening today, is cloud spending. So 2019 was the first year that spending in the cloud, so AWS, Azure, Google, Baidu, Tencent, cloud spending was bigger than on-prem data centers. The trend was the trend already, but you can see we blew past in the year of the pandemic. Everything is shifting into cloud. And one of the things I run at Silicon Labs is IT, and I can tell you almost every single thing we do now is SaaS-based cloud apps. There's only a couple left in our own data center. We do our own chip design. Maybe one day that'll go to the cloud, and we have SAP running in our data center. So everything else is shifted to the cloud. So it scales much more easily. The fourth piece that's important, it's remember, these computers are everywhere. People want to connect them to the internet. The infrastructure to do so is out there, but how hard is it? Really, how hard is it? And this is where Silicon Labs comes in, and where I've been spending the bulk of my career is reducing the barriers to connect those devices and manage them. That's the other piece here. And I'm going to walk you through four trends on specific time instances that are enabling this. The first is compute. These are computers after all. What's happening on the processing side. The second is on connectivity. Again, you got to get this device, you got to get the data off the device somehow. Third is, and we're living through this one now, security. So once you have a computer that's connected, you have to secure it. Every other platform has gone through this. Things like your PCs. I remember in the 90s, malware and banner ads and all this kind of stuff happening. And then on mobile phones as well, especially prior to about 5-7 years ago. So you got to secure these things. And then the next phase where we're heading into right now is making these devices truly smart. And this is where machine learning and a lot of the work that's going on at UT, actually in Diana's group especially, it comes into the fold. So let's go into the first piece here with compute. And you're going to see a kind of a framework that includes a prior state, a catalyst, today's state, and then some descriptions. So in compute, it's been about standardizing on the ISA, the instruction set architecture for CPUs and IoT. Prior to the mid 2000s, everything was proprietary out there. AVRs, MSPs, PIC, Power PCs, Renaissance. When I was at UT, we were coding on Motorola 68,000 microcontrollers as part of our microcontroller class. I bet I don't know what it's on, but I'm guessing it's on an ARM core today. But then something happened in the mid 2000s, and I looked for this catalyst event, and I timed it to ST's announcement of the Cortex M3 CPU license from ARM, and that set us down a path in the embedded space where the proprietary architectures lost share. What was a highly fragmented proprietary market with code compatible, you couldn't port code between manufacturers, turned into something that you could. I'll show you an example in a second. But the kind of chips that were floating around in the IoT at this time ran with one CPU core with about 128 to 256K of flash and less RAM, low clock speeds, and pretty old technologies at this point, like 180 nanometer. This is not cutting edge 7 nanometer, 5 nanometer stuff coming out of TSMC right now. As my proof point to this, I plotted out the MCU shipments, Cortex M MCU shipments, which really went from 0 to about 1 billion units in MCU over about 4 years. And that's very fast in the MCU world. MCU world doesn't run as fast as PCs or cell phones. It's a little slower. It's not as slow as automotive, but it's slower than PC. And then that was out to 2014. And then today we get to, well, what is most common? And ARM has kind of won this, at least for the vast majority of the market. So, and at this 2019 embedded market study, 8 out of the top 10 answers to this question was an ARM architecture, some MIPS and some AVR left over. I mean, one thing that is coming to challenge this paradigm maybe is RISC-V. If you haven't heard about RISC-V, you probably will while you're in school, but it's a new ISA that is open source. And we are using that at Silicon Labs. We're using ARM cores. We're using 8051s, believe it or not. We use all kinds of cores for different reasons, but we'll see where the RISC-V goes. Next is on connectivity. So at the end of 2011, kind of what was starting. From 2012 to 2016, connectivity went through a rapid growth phase. And it's a similar story on standardization. That prior to the 2010s, call it, most connectivity in embedded applications was proprietary. Remember, I'm not talking about PCs. PCs had Wi-Fi, and cell phones, smartphones were starting to get Wi-Fi. But in embedded, it was mostly proprietary. No interoperability, multi-chip solutions. It was very inefficient. My catalyst moment for this was the launch or the announcement of the iPhone 4S in 2011, which was the first native OS to support Bluetooth Low Energy Standard, BLE, Bluetooth 4.0. There were some phones running Android prior to that, but it wasn't natively supported within the OS. It was written on top, and it was very bulky and didn't work very well. So all that BLE stuff that you see now, it was invented only in the last decade. The result of this is that we see standardization, interoperability, ecosystems emerge, big alliances, basically in volume increasing in the market. You can see that volume here on the right, where we see the pickup of Bluetooth Low Energy and cellular in the smartphone space go from 0 to 1 billion pretty quick. And then you see a lag on the embedded side where we are continuing to increase year after year. So smartphones only gets to a certain point. There's only going to be about 2 billion that are shipped a year because there's only a certain amount of people on the planet, and I only have 2 hands. I don't know about you, I can only hold 2 phones. But embedded is going to grow forever. For all intents and purposes, forever. There's no reason we can't see 100 billion embedded Bluetooth devices shipping on an annual basis. So it will be much, 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 much larger than the cellular market. So what kind of chips we're shipping at this time? We're starting to see more CPU cores, more memory, higher clock speeds, finer process geometries, and MCU and radio integration onto one SoC. So no more multi-chip, down into single SoCs. I'm gonna keep going. Next is in security. So we are now in the phase, or we've done the hard work really in the chip world over the last 5 years to start securing these devices. And that's a really big deal because you see this news here on the right. I mean, it's not the hardest thing to hack some of these IoT devices. And I don't mean just low cost ones, I mean cars. I mean, there's a famous hack where hackers could disable a Jeep while someone was driving it on the highway. This was a few years ago, but it's still happening now. This is very recent. Tesla, someone published, a researcher published a hack where they could remotely take it over over Wi-Fi, believe it or not, as long as you were close enough. So they were using drones to go around and find these Teslas. So it's not just about safety and access, it's about your health. I mean, there's a lot of reasons you want to secure these devices, any device that is connectable from a remote distance from the cloud. And we're doing a lot of that work at Silicon Labs, and we're doing it with more complex devices, more software, so more CPUs, more memory, more. I mean, that's kind of Moore's law, pun intended. What we go out and do. What we did at Silicon Labs was we completely re-architected our entire system on chip architecture with a secure core at its heart, running everything. So the customer has access to certain pieces of it through well-defined APIs, but we use that root of trust, hardware root of trust, with a lot of public key infrastructure we build up in our supply chain to securely manage and ensure that these devices are about as protected as they can be. The catalyst moment for this, by the way, is I picked one back in 2017. ARM launched their PSA certification program. PSA stands for Platform Security Architecture. And over time now, we're starting to see the MCU companies embed dedicated security processors into their chip. And it's not easy to do that, but it's happening, and I'm really glad, because I want my IoT devices to be secure. The last piece, and where this has been going since day one, is making this stuff useful, making it smart. And we're in the middle of doing that right now as an industry, all the chip companies right now. So I don't have a catalyst. I don't know what it is. And maybe it has happened, maybe it hasn't. I'll have to figure that out. Ask me in a few years. But before, there's not much processing on these devices. It's very if this then that CPU based kind of processing. And so most of the data the devices are collecting has to be sent to the cloud. So a lot of the networks are flooded with garbage data, because most of it is garbage. And frankly, the network bandwidth itself is very limited because you're sending so much damn data. Excuse my language. You're sending so much data the whole time. So network bandwidth is the most precious resource in an IoT network. And so you only want to send the things you need to send. So we are doing a lot of work. We have launched some of it, and some of it we have not. But the result of all this is that the computing will distribute between the cloud gateway and edge nodes. And Deanna has a great example where she's asking her smartwatch questions as it's not connected to the internet, and eventually it'll be able to answer you. And we're building those chips right now. So more cores with dedicated machine learning acceleration, more memory, finer pitch geometries, and we're going to do really cool stuff with this. We're going to make the products better. We're going to make them safer, easier to manage. Little tiny things. Smartwatch, a PIR sensor, a coffee machine. So this is really, really exciting. It's on the forefront of a lot of a decade of research, and ML is now coming straight hard at embedded. So if you add up all these dots, it's going to tell you something. And this is what it's going to tell you, that most embedded computing is moving from offline to online. And that's a paradigm shift that we are in the early phases of. And so I showed you this MCU data in the past, and I'm showing you now what industry analysts are projecting. So this is based on AMD and WSTF's data, how big it's going to go. And I don't know if there will be even a reason to stop. I don't know how big it'll be. Maybe it's 50 billion a year or 100, which is hard to imagine, but it was hard to imagine 15 billion units a year at one point as well. So we are here, and this is the wireless MCU. MCU and wireless are overlapping Venn diagrams in this world. There's a lot of similarities, but there's also a lot of differences that come into the play. So it's really exciting time to be in lining these dots up and playing the trends out over time. I love doing it. I love building the technology that we're building. We're building everything from transistor level design out through cloud software and everything in between, embedded software, tools, PC, mobile app, even the products we're building to manage a supply chain securely are very exciting. And many semiconductor companies are doing this as well. There's when I started my career in semiconductors, it was very stratified. Semiconductors only did up to a point, and then you sold your product, and your customer would take it and do more and more and more. Those lines are blurring now. The idea of a semiconductor company doing cloud software, or the customers demanding that you do cloud software, 20 years ago when I was getting into it, was just very foreign. I think maybe Intel and a couple of others had visions of this, but they weren't doing it. And so now you start to see all the multidisciplined nature of what we do and what we learn in school. And I'm going to talk about school now in a second, come together. And so I think the most interesting technology innovations on the planet right now are happening at the hardware software interface. It's not enough to locally optimize, software independent of hardware or hardware independent of software. You have to do more global optimization problem to get the best solution. So with that, I'm going to move into the next part of the talk, and this is, a little bit of advice. Actually, I guess is the best way to put it, because I get asked these questions a lot by people, and so I figured some of that would come up here, and I hope you have other questions. But I would like to ask everybody to strongly consider building a very diverse collegiate experience. And this doesn't matter if you're a graduate student or an undergraduate student. While you're at UT, you have probably the best opportunity in your life in terms of raw diversity, raw number of things you could go do right now. And I just wanted to share a little bit about my experience. I didn't plan to do it this way, but this is what ended up happening for me, is that I came into school actually as a mechanical engineering major. And I switched to double E pretty quickly. I think it was thermodynamics and reading steam tables in the back of a book. We didn't have all the tablets and things like that back then. So I switched over to double E, and I just fell in love with it. And I ended up spending a ton of time. And this is the old building where it's gone now. This is the old ENS building. I had a lot of fond memories there, and I remember when it was getting torn down. I was like glad that's great for the students, but I also had some fond things, and I spent a lot of time there. We'll talk about time in a second. But that wasn't all I did. I didn't just my college experience wasn't the sum of my course load. I did more. I spent a ton of time in music, and when I entered school, I actually thought I was going to do music or switch into it. And I had really fortunate experience to play with under Jerry Junkin and his wind ensemble, and in chamber groups and in private lessons. And I spent probably more time in the music school my first couple of years than anywhere else. And it was very formative for me. You learn a lot of discipline in music, and gives you a lot of appreciation for making, getting things right. In music, there's pure talent, but then there's no substitute for putting the hard work in. And that is a lesson that I carried into my engineering career, is that there are no shortcuts. And you got to be very careful about assuming that there are. So I invited him to the talk. I don't know if he's here, but it was a very important part of my college experience. And I still think about some of the performances that we have. Last, but certainly not least, I did something completely different, which was I rowed on the rowing team. And this is just a little photo I found back in 2002. And there's some chat coming in. There's me, believe it or not. And I spent a ton of time in rowing on Town Lake, and training and traveling, going to Boston, going to San Diego, going to kind of these really old races where you could see a lot. It's just a totally different world than anything like music or anything like engineering. And again, no shortcuts. You got to sit down on that erg and you got to pull and you got to row and you got to be with your team. And this is where I really got drilled on teamwork and how to move a boat fast and the dynamics there, which is more important in engineering now than it's ever been. There is no such thing as the single person who's going to move a mountain in an engineering company at this point. It's all team based, and in some cases, as knowledge workers, getting the team dynamics right, regardless of the sum of the individuals, is the most important thing. So I learned that. So spent a lot of time doing this. I was trying to figure out how many hours it was because I like to quantify things, and I decided there's only 1,000 hours a year of work when you're in college, because you have summers and you have breaks and all of that. Usually it's 2,000 hours, but it's 1,000 because of all the breaks. And I figured I spent like one third, and I don't know where the other third is. Maybe it was taking the bus or tutoring or something like that. But you got to put time in, and when you look back over your time in school, I hope that you see other kinds of our society, basically, because as you move into engineering as a career, whether it's in academia or if it's in the industry, you start to get more and more segmented in your own little world. So I encourage everybody to get what they can while they're in school. And Jerry, I see you on chat. I'm glad you're here. Thank you for joining. So moving on to the career management piece, there's a whole industry dedicated to this stuff. I carry two things at the forefront today. I wish I had earlier in life, but just wanted to share those. The first is this idea of long periods of time. And there's the famous quote, I'm sure many people have heard it, but if you haven't, it's that the best time to plant a tree is 20 years ago. The second best time is now. And the way I interpret it is that you can say this about any factor of your life, but when it comes to your career, it's that there are certain things you can do that accumulate or compound over long periods of time. And when you're younger, or when I was younger, I didn't think over long periods of time. I never thought I'm going to be here in 10 years. I'm going to be here in 20 years or 50 years. And but bottom line is you will. I hope everybody can say, yeah, I'll still be here in 10 years doing something, or 20 years or doing something. And the question is, what will that future version of you look back and wish you did 20 years ago? So that's one thing, this concept of time domain or temporal state. The second is that, man, there's infinite resources out there. You have to fall over yourself. I mean, there's more than you could ever consume in a lifetime. And so you got to be careful about who you listen to and what you go look for. And these are just digital resources. There's a lot of offline things out there too. But I'm not as good at almost anything as the experts you can find in these places. So use that. Use those resources, Wikipedia or Google. I give money every month to Wikipedia because I think it's just the best thing on the planet, or one of the best things on the planet. But use these resources. Don't be afraid to do that. This idea that you have to sit in a little ivory tower and design everything from first principle is just false. You don't have to do that. You do need to understand the principles, and you do need to be able to do that, but that doesn't mean you're going to do that for everything. In fact, you shouldn't be doing it for most things. So think over long periods of time, use the resources that exist. None of this existed when I was in school. Google, I remember Google got popular in the middle of my time at UT. And I don't even know how. I think I was using Alta Vista or Lycos or who knows what, message boards to find stuff before then. It was just, it changed everything. So my last topic here is actually some career advice. This is not really advice. This is just principles. Here's some advice. And these are things that I think don't get enough airtime, because there's a lot of things that get airtime and these don't. And the reason I tried to figure out for the longest time why they don't get enough, and it's because it's not immediate in a lot of cases. The benefits are not immediate. And people like to do things where they can see the immediate benefit. So these are, you have to have more patience. The first is mentorship. And I can't overstate how beneficial that's been for me. And I like being a mentor. I mentor people. But I always say, find a mentor and be a mentor. Don't forget about the be a mentor part. Because experience matters in all of this. Especially as you go deeper into your career, it becomes very experiential at some point. And having been there, done that is a great thing. But many people haven't been there and done that. So find people who have. They're great at pattern matching. They're great at predicting what will happen because they've kind of seen the story play out multiple times. Second thing here is that the most successful people, and I'd argue all successful people, have mentors. It's not bad to have a mentor. It doesn't mean you're not good. It means you actually value the things that mentors have. So I've talked to a lot of successful people, and I've always asked, did you have mentors? Did you have mentors? Do you mentor? And the answer is always absolutely. Third, mentors like doing it. Don't feel afraid to reach out to someone. And literally, you could send them an email and say, would you be my mentor? Promise you, you'll get a lot of responses that you may not think you do, because the people who mentor actually like it. And this is something you can start now. You get the benefits of it over time, but it's something you can start. Maybe you don't know where to find a mentor, but be a mentor. Go tutor at ECEC. We used to have ECAC tutoring, or go call your high school or wherever you came from. Just, you can be a mentor. You can start doing that. And there's a question right here on how to know if someone's the right mentor, coming in from Ragav. I would say to that, ask is the best way. If you think someone might be it, just ask them. You'll either be right or wrong, and you can just feedback that loop and just iterate over time. There's the worst someone can say is, I don't have time. And that's not a bad thing. That means, okay, that's not my mentor. So mentorship. Next one is on a risk tolerance. And this is someone's asking, is it too late to find a mentor? It's never too late to find a mentor. That's an easy answer. A senior undergrad, doesn't matter what, I have mentors today, and I continue to reach out. It just means you value what people who've been there have done. That's all it means. So let's move to risk tolerance. On this, first, initial conditions really, really matter with your ability to take risk. And this is where not all people have had the same background, or have had the same benefits, or have had the same bad things happen to them. So you got to start with where you're at and really be honest with yourself about it. And some people can take a lot of risk, and maybe you can't. Maybe you're in school, but you're taking care of your family. Maybe you're in school, but you have you're on a visa. I mean, I've been on visas in other countries. That kind of sometimes restrains what you can do. Your initial conditions matter. That's all I'm saying. I just don't, I don't want to say, everybody should have the same kind of risk. That's just not true. What I have found is that taking risk earlier in your career is easier than later. And that's not true in every case, but it's true in many cases, because life happens. People do get sick, people die, you get married, you have kids. I have 3 young kids. There's things that I can do 15 years ago that I just can't do today because I need to be there for my family. So, it's funny because taking risk is easier when you've failed in the past. But your ability to take risk maximizes before you failed. So it's this weird optimization problem. rounding this out, be ready for opportunity. Like, you can't necessarily predict everything, but you got to be ready. You got to be ready to take that risk. You have to have the conversation with yourself before something comes at you, to be ready to do it. And last, let the world surprise you. You can't predict everything. Be ready when something funny happens and an opportunity presents itself, to realize what it is and not ignore it. Don't put the blinders on necessarily, and not see what's out there. And my last thing, before we get to hopefully some Q&A and some chat with Deanna, never, ever, ever let your curiosity die. This is something that wasn't obvious to me until later in my career. And frankly, I'm still mid-career, but you cannot be the best. You cannot push state of the art unless you're curious about it. And there's a high correlation to being curious and success out there. But people who do meaningful work, and I think most people here would raise their hand and say they want to do meaningful work. You can't get to where you want to go. You can't get to being to the point where you're at the forefront of what needs to be learned and done unless you can sit down and really look at it and say, wow, that's kind of interesting. Why is it this way? Why? And actually have the tools to go out and figure out why. And sometimes it gets really, really hard. I mean, there's a lot of dead ends. And I think in academia, especially, it's very lonely. You have to have the energy to keep going. And the curiosity is kind of that energy to me. A very important thing here is that you start to see the connections, subtle connections between stuff. I'll just leave it at that. If you just constantly asking yourself why, and then going and figuring it out and just feeding that, you'll start to see a lot of things connect. And then lastly, if you do lose it, it's hard or impossible to reignite. I've seen a lot of people get to the point where they just stop questioning anything, and some of the spirit and value kind of flies out the window at that moment. And I don't know if they get it back or not. I know that I feed my curiosity every day in some way. It doesn't have to be hours of reading a book. I wish I had more time for that. I don't anymore. But you can find little things to do. So that's it here for the talk. I covered some technology and how to line up where you point your innovation engine at. And I went through some ways to think about your time at UT. And welcome back, everybody. I know that this is what this event is, so welcome. And then as some things to think about, especially while you're a student, to managing your overall career, whatever that looks like. It may not be in engineering, frankly. I know a lot of engineers who get out and they don't actually engineer, and they still carry forward a lot of the things they took from school. So I will turn it back to, I'll stop sharing here and turn it back over to Deanna, and maybe we can have some questions.
Thank you so much, Daniel. This was such an inspiring keynote, and I'm sure many of our students and our attendees have more questions. In fact, there's a question asked about how can we find a mentor in our discipline, specifically in software engineering or data analytics.
Oh, sorry, getting a drink there. Good question. So in general, how to find domain-specific mentorship. It depends on the domain, frankly. I don't have a great answer for software and data analytics. Maybe you can follow up with me on an email and I can point you in a good direction there. Just off the cuff, I don't have a perfect answer for that. I apologize. Why don't we take another one?
Well, I can suggest, students should reach out to faculty in that area, and perhaps more senior students. Peer mentoring always is an option. And of course, if they reach out to you, Daniel, I'm sure you'll also be able to help them.
I've never not answered the question.
Right, I'm sure. Willie has a question. Why were there not concerns about security until everything was connected? And why do you think security will end this year?
A great question. There were concerns about security always. The problem is once a device is available for remote hacking, the number of people trying to hack it goes up exponentially. So for example, I've got a Nest thermostat sitting there on the wall. If it wasn't connected to the internet, I'm not too concerned about someone being able to break into it. If it is connected to the internet, I do worry about that. So it's the remote attack angle. There are local attacks that are obviously concerning in a lot of applications, like a payment system or a medical device in a hospital. But it's the remote attack capability that makes it big. And I don't think security will end this year. What I was trying to show was 4 phases that line up in connecting dots in leading to something. And so it's happening. It's not ending. It's just a lot of the work that we've been doing in the semiconductor IoT space. We're building on foundation now instead of building on nothing. So we have a lot of good stuff to build from. And what seat was I in crew? So I'm not the tallest guy on the team. I was either in the bow or the stern. So I rode 2-seat or 8. So my last couple of years, I was the stroke of the boat, which was fun. On my first 2 years, I definitely was, and I was getting in shape.
More questions? You can use the chat or you can use the Q&A. Maybe I can ask a more general question, Daniel. So you talked about the different phases. We're now in the smart, or identifying how our devices can become smart, or how can we exploit or explore the possibilities of that happening. What do you think will be the challenges or the different things that will come in the future? So, for example, is privacy or designing or engineering systems with ethics in mind something that needs to be explicitly considered? Are there other things that, obviously everything around us, especially when we talk about IoT, have to be energy efficient. Are there things that we need to be even more mindful about when we design systems?
Yeah, you're starting to touch on a big topic. Absolutely, I think ethics has a big role in artificial intelligence in general. I don't want to turn a banking decision over to an AI that maybe has implicit biases that are wrong, as an example. So ethics has to be there, and I know there's big teams at places like Google looking at that kind of stuff. In IoT specifically, what we're starting from basically zero at this point. So you're starting to see the first products launch into the market with a basic machine learning accelerator. So, taking it out of software and finally having something that can run some of the math 10x better or 10x lower power, and starting to do, higher value algorithms as a result. So we're at the point now where it's basically basic inference on these devices, looking for events, whether it's a simple word that someone speaks into a microphone, or detecting a vibration on a motor that's, okay, the motor's starting to something's wrong. Go get that before the motor destroys itself. Or a microphone, like listening for something like a gunshot or a window breaking. People have been trying to do this functionality for a long time. Now they have this new tool and they're using it. From there, we're going to go pretty far, I think, in the end, to the point where a lot of the intelligence doesn't have to even get to the cloud for action. And it can be more private. I don't know if it will. We'll have to see. That's more about government regulation than what the technologies are capable of. I personally hope we do have privacy. I don't like the idea of 1984. That then again, I use my Alexa and Amazon's listening to everything I do. So, it's kind of going to be that trade-off on what people are willing to accept.
We have a question from Ryan. Why choose Silicon Labs versus another silicon company?
Good question. So it's funny. When I started looking for internships, was in the depths of the .com bust, and let's just say it was not a great time to be going and looking for jobs. And in fact, I had failed so it was my second year, and I had pretty good GPA, but I had switched majors, and so I was a little earlier in my course track than most other people in their second year. I didn't get it. I didn't get an internship that fall, and I got a lot of interviews because I had good GPA, but no one was picking me. And I had a job at Barnes and Noble, where the bookstore is on the drag, and I got a call from one last company, Silicon Labs, at the last minute had decided to do an intern program, and I raised my hand and went in and interviewed, and I got one of the spots. There was only 3, I think, that summer. And so I didn't set out to join a silicon company. I set out to get a job. But I quickly realized it was a really lucky place to land some of the best engineers in mixed signal RF design in the industry at a time when doing that in CMOS was questioned. Many companies were still trying to do it in bi-CMOS, or heaven forbid bipolar. And so I was learning about all this mixed signal techniques, and if you really want to know, one important thing was a mentor there. It was a guy named Jan Tesu, who was a professor in Romania before he came to the US, and he actually invited me to come back during the semester, and he would give me supplemental instruction for 2 hours a week for analog chip design. And so I was learning cascoding and source followers and the noise and even mixers and all this other kind of stuff ahead of the class. And so it was the people and kind of that stuff. And I mean, at one point I was wondering if semiconductors was where it was going to go long run, and I didn't know if it was all going to be software running on my chips or whatever. And now it's super exciting because we're writing our own code for our own chips. So that's a little bit about the story there. But it started as an internship. So I'm an NCG, new college grad at Silicon Labs in the early 2000s.
A question from Matthew: what goals did you have leaving college?
So when I left UT, I was going to graduate school. My goal was to do well in graduate school. I knew I was coming back to Austin because Silicon Labs was actually they paid for my graduate school. And so I knew I had a job lined up. My goal was to learn as much as I could and have a full college experience while I was in grad school. But maybe your question is really just, as I was heading into my career, what was my goals? To get good at what I was doing. Don't think you can just come in and be good right away. Most of the time you come in and you have a lot to learn, and being open to that was big. So I wanted to get good, and someone had once told me it takes 5 years to get good at something. And so I was like, I'm not going to try to set a timeline here. I just want to be a really, really, really good chip designer. And so I set my energy to doing that. Beyond that, in terms of my life, I didn't really have goals to get married by a certain time or buy a house or any of that. I just really wanted to have fun with my friends and be good at what I do. It was very simple.
Great, thank you. We have a couple of related questions. Perhaps it's the last one. Ryan Root asks, rather than what will change in IoT and embedded computing in the coming years, which aspects of the field you think won't change? And from Anna Claire, what are your thoughts on how sustainability may progress in the near future on the IoT industry?
Good question. I think consumers don't want to see the technology. They don't care about it. There's some people that think it's cool to have the latest, I got a Wi-Fi 6 access point in my house doing Wi-Fi. Most people don't care. They just want their stuff to do more of it and better. Whether it's, I have a couch, they want it to be a better couch, or I have a TV, I want it to be a better TV. The real trick is like cars, you don't necessarily want to get in your car and you're not going to buy a car for the engine. Some people do, but most people don't. And so finding a way to connect the technology to what people care about without pushing the technology to the front, because the technology is only there to enable something, enable a function. It's not to be the thing itself. So what's not going to change that? No one wants to see the technology. They want all the benefits from it, but the consumer doesn't care in the end, and nor should they. And they never have. And that's not bad. It's just the way it is. And then so there was a question on sustainability. I don't remember exactly what it was. I do want to hit that.
How So the question was on how sustainability may progress in the near future of the IoT industry.
Well, I'm going to interpret this question as, is the IoT going to grow? Like, is it a sustainable growth path? It is. And there's a lot of data showing it. I won't go into excruciating detail. You can hit our investor relations page at Silicon Labs if you want to know, because we're investing a lot to be a lot bigger. But the embedded CPUs that are out there are connecting to the internet at an increasing rate. And there's new applications that are emerging that don't have MCUs that are now coming. Like, think about a pallet or a tire, or I mean, so many things that have never been connected. The paper shelf label that turned into an electronic shelf label. There was no MCU there. It immediately was something connected to the internet. So the growth's there. It's going to grow 10x, 100x. I don't know. There's not many industries that are doing that right now, which is one of the reasons it's so exciting. There's so much greenfield out there, and not to say that the other places are not. I mean, what's happening in the data center is amazing, and smartphones is kind of consolidated. There's only a couple of companies, and PCs are similar, but automotive is big. I mean, 5G. I mean, there's so many good things happening. You're in a really, really, really good spot entering, being in school when you are. Like that's in many ways lucky. So I look forward to seeing what you're going to be able to get done.
Hey, well, we're actually over time, so I would like to thank again Daniel for being here and for giving us the closing keynote for the Welcome Week. It was a really inspiring talk. Thank you all for coming. Thank you for attending, and thank you for all the insightful questions. Again, thanks, Daniel. Welcome, everyone. Have a great semester.
Thank you, everyone. Thank you, Diana.
Thank you.